Boldly going where no science show has gone before. The Naked Scientists.
Hello and welcome to The Naked Scientist with me, Ben Valsler, and with Helen Scales.
Hello.
Today we're looking at the science of architecture. That's the science of designing and building our homes, offices and every other type of building. We'll be hearing how rapid prototyping technology could be used as an immense 3D printer to print out entire houses, and how natural light and ventilation could keep buildings light and airy, as well as reducing bills and energy use.
Plus, we've got lots of news from the animal kingdom. We find out how birds learn from their neighbours, but only when the lessons are right, how a squid's entire body acts as a giant eyeball, and we listen to some chimps being tickled. Isn't that wonderful? Doesn't that just make you want to laugh too? That's the sound of a chimp being tickled and laughing. And coming up, we'll also find out whether or not that tells us anything about our own tendency to giggle and how that evolved.
It is quite addictive, the sound of a chimp laughing, isn't it? Plus, in Kitchen Science, Dave and I will be challenging you, our listeners, to build the best bridge you can, but you're only allowed to use a single sheet of A4 paper.
If you've got any questions at all or comments for us, then do get in touch. You can call us on 0845 30 50 007 or send us a text 07786 20 1960. And if you want to email us any questions at all, send them in right now to chris@thenakedscientist.com.
The Naked Scientist Podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Now, we have an awful lot of news from the wonderful animal kingdom this week. And firstly, laughter is a wonderful thing to hear. But the question is, would you recognise it if you heard it coming from anything other than a human? Now, we know that apparently hyenas laugh, but I doubt they're doing it because they find something funny. So it's very interesting to try and work out how these things have evolved. In a delightful study published in this week's Current Biology, Marie de Villa-Ross and colleagues at the University of Plymouth have found out that what we think of as laughter today could have evolved in our common ancestor with the apes somewhere between 10 and 16 million years ago. To test this out, they've been listening to the sounds that were made by 21 young apes when they were tickled and comparing them to the sounds of a human baby being tickled. The sounds were then subject to an acoustic analysis that could detect similarities and differences between the sounds, and importantly could judge how closely related these different sounds were.
It just sounds like a wonderful study. I wish I had been the one who could do the tickling. Whose job was that? But there's a picture, isn't there, I think, in the paper. At least I saw on the website of the orangutan being tickled. It just looked fantastic. But what were they looking for in these sounds?
Well, first of all, let's just have a listen to some of them. Firstly, we've got a chimpanzee laughing. That's a lovely one, isn't it? And now we have a tickled gorilla. That's really very different from the chimpanzee,
isn't it? Yeah.
And now one that should be altogether a bit more familiar to most people. This is a tickled human baby.
Oh, isn't that gorgeous? Wonderful.
It is. Now, all in all, they analysed a total of 829 recordings, and they looked at 11 different acoustic aspects of these sounds. So these were things like the frequency, the range of frequencies, the number of calls and about. They're all in the paper. It lists actually what these were. And they also looked at whether the sounds were made on the inhale, so a sort of noise, or on the exhale, as when we speak, or in fact on both.
And what did they find?
Well, they found that there were a great number of similarities, but also some key differences. It turns out that we humans are actually much noisier than our ape cousins, which is good when you're on radio, as the human babies produce significantly more voiced sounds. Now, these are sounds that clearly come from regular vibration of vocal cords rather than just a type noise.
Oh, I see. Okay, so kind of more deeper down in the throat almost.
Yes, yeah, so voiced meaning from the voice box rather than just a pant.
Right.
And the human babies also only laughed on the exhale. They didn't laugh when breathing in, while the other apes could laugh both when breathing in and breathing out. There was a surprise finding that while they were laughing, the chimps and the bonobos, which are very closely related to chimps, could effectively control the rate at which they breathe out. Now, that might not seem very surprising, but it's thought to be a uniquely human adaptation that allows us to speak. So normally when animals vocalise, they just breathe in and out at the same rate that they do when they're not vocalising. And being able to control it, you and I at home, when we breathe, we don't have to breathe in and out at the same rate. I'm making this breath last a very long time to make this endless seeming sentence with no punctuation going on, and I can still keep on going, and I haven't had to breathe in yet. And
oh, you do eventually.
eventually, yes.
Yes, okay.
Now, also interestingly, the differences seen for human babies were not one end of a spectrum. So it's not like humans are one end of it and then the differences fade out gradually as you get. The differences for humans were sort of inconsistent with the differences for other apes. So otherwise, between all the other apes, it's quite hard to tell one from another, and then humans seem a bit distinct. So next, they put all of this data together to see how closely related the sounds were and created a family tree of laughter.
So they kind of fitted the differences in the sounds to differences that we see genetically between all these different species.
Well, we can use the genetics to build a phylogenetic tree. It shows how closely related things are. And they effectively, they ignored the genetics for now and just built a similar table for the relationship between the different laughs. And this laugh tree actually fit the genetic tree extremely well. It showed that Siamang and orangutan laughs were more similar to each other than they are to all of the other apes, and in fact genetically they're more similar to each other than they are to the other apes. As chimps and bonobos are the same, they're closer to each other than they are to us, and humans laugh more like the chimps than they do like the other apes, and that also fits our genetic relationships. Now, it's all too easy to fall into the trap of ascribing human thoughts, intentions and emotions to animals. We think of foxes as being sly. Very often I see my cat fall off a window ledge and then look round, and I honestly think he's going, "What? I meant to do that. That was what I intended."
An embarrassed cat.
Yes, exactly. No, this is called anthropomorphism. This is when you ascribe human thoughts and intentions to an animal. But this paper now shows that when an ape is laughing, it's actually okay to call it a laugh. And this reminds me of a lovely joke I heard recently, and I hope you'll get this at home, and that's that you should never anthropomorphise animals, because they really don't like it.
Oh dear, does that make you laugh like a chimpanzee? I don't know. Anyway, I'm going to stay in the world of animals for my story, which is about those fantastic denizens of the deep, squid. And the fact that scientists have found that they don't actually only see through their enormous round eyes, but also all the way along their bodies as well. And this is a paper that's been published in the journal PNAS this week by researchers from the University of Wisconsin-Madison in the States. And they've been looking at the underside of a Hawaiian bobtail squid. And these are really cute. Seriously, check out a picture of them. They're about 3 centimetres or an inch long, and as far as squid go, they are really quite gorgeous little things. And what they have is on their ink sac, which normally just releases ink when they want to stun predators or confuse them when something's come to eat them. They actually also glow, and the reason they do that is because of something which is known as counter-illumination. When a predator looks up at that squid from the underside, normally it would see a very dark outline against the brightness of the surface of the water. But in fact, when they glow like that, it means that they blend in. Really, they don't show up as a dark shadow against the surface of the water. And now Margaret McFarlane-Guy and her team have found evidence that those camouflage organs in the ink sacs are actually capable of not just emitting but also detecting light as well.
That's really incredible. I mean, this sort of camouflage is amazing, to be able to cancel out your own shadow, to mean that things underneath you just can't tell you're there. But how does it work? How do the squid make that light?
Well, it comes out of a type of bacteria called Vibrio fischeri, and that was discovered about 20 years ago. And they naturally glow, and this is in a process called bioluminescence, and it's a really good example of a symbiotic relationship in which 2 species live together, and they both benefit from the arrangement. The squid have this wonderful camouflage that the bacteria give them, sort of an invisibility cloak, if you like, if you're a Harry Potter fan. And in return, the bacteria get a nice, safe place to live and with all the nutrients that they need.
Right, but surely if it's a different animal, as it were, or bacteria, then that will produce light regardless, because that's what it does. But how does the squid control it? Surely the squid needs to regulate that light.
Yes, they're not just glowing all the time. And in fact, the tissues around the ink sac that contain these bacteria actually have the ability to kind of close in around them. That's really much like an eye. It's quite extraordinary. Like the iris in your eye can change how much light gets in. This is actually controlling how much light gets out. And they're even covered over the top of the ink sac with a rudimentary lens, a clear layer. And that even kind of focuses the light a bit like a lens in your eye. So the squid really are able to match themselves very carefully to the brightness of the sea surface, because that'll change with the time of day and where they are in the world and so on.
Well, I guess it makes sense, because if they need to know how bright it is around them in order to know how to cancel out their shadow, it makes sense that these bits can also detect light as well as emit it.
Yeah, that's absolutely right. And what these researchers have done is they looked at those ink sac tissues, and they found that there are genes in those tissues that are also associated that produce proteins that we also find in eyes that are really associated with light detection in the retina. And they also looked at these light organs, and they shone light at them and measured the response with an electroretinogram. And that's basically an electrode that you'd normally measure the response of a retina when light is shone on it. But they did the same thing with these ink sac tissues and found that very similar electric signals were also generated by these light organs in the squid. And that gives a really good indication that not only are they producing light from these bacteria that they're living with, but they are actually sensitive to light as well.
So could this actually be how vision evolved in the first place, in this sort of diffuse sheet of light detection? And we know that it eventually got co-opted into interesting structures like eyes, but could this actually tell us a bit about how vision evolved?
It certainly could, and I think the researchers at the moment don't really know exactly how the eyes of a squid are related to these ink sac structures and how that came about, but it could be a form of something called evolutionary or genetic tinkering, and that's a technical term. I think that's wonderful, and that's really sort of the co-opting of an existing system, an existing set of proteins and so on that are working to produce a certain effect, in this case capturing light. And that could be what's going on. But we do need more studies to delve a bit deeper into exactly how it is that squid have eyes, and they also have potentially have this ability to detect light all the way along the bottom. And I think it also gives us some insight into this symbiotic relationship with bacteria, because we are also big animals that have a very intimate relationship with lots of bugs, because 8 out of 10, in fact, of our internal major organs have some sort of bacteria living in them. They might not produce shining light. That might be quite fun if they did, but we do rely on them, and they do keep us healthy. So understanding more about how different animals and species have lived together and evolved to live together is really quite important for understanding our own health, I think.
That's fascinating. And it's probably for the best that actually the bacteria inside us don't produce light, because then there's only sort of one route through which it could shine out.
Yes, indeed.
Right.
Food for thought, I think.
Now, back in February, I reported on a paper in the journal Current Biology about how birds called reed warblers protect themselves from being parasitised by cuckoos. And in a follow-up paper in this week's Science journal, Nick Davies and Justin Velbergen from Cambridge University have found out how these birds learn to defend themselves. And they do it by watching their neighbours. Now, as I'm sure most people know, cuckoos are a problem because they lay their eggs in other birds' nests, and so they let other birds bring them up. It wastes a lot of energy for these reed warblers, and there's no advantage to them. They're not passing their genes on. As a result, they've evolved a tendency to mob the cuckoos, which makes them less likely to end up being parasitised. But it is quite costly, it takes a lot of energy, and it risks exposing themselves to the predators.
So what do they actually do? Do they sort of gang up together and shout and scare the cuckoos away? Is that what these reed warblers are up to?
Well, what they do is they make very loud calls and they snap their beaks with a loud clicking sound. In fact, we have a recording of it here. So they're shouting. That sort of sharp knitting needle clicking is them snapping their beak really hard. And they also swoop down at the cuckoos. They physically attack them, and they generally get in quite a flap.
That does sound quite scary if you're a cuckoo, but and it seems fairly sensible for these reed warblers to get upset. But what's new in this science paper?
Well, in the new paper, they present evidence as to how the warblers actually learn when to mob and when not to mob. Because it's a bad idea to waste your efforts mobbing a bird that isn't a threat, and if there's a predator nearby, you make yourself really obvious. That's a very loud thing to happen. So armed with a model of a cuckoo and a model of a parrot.
A parrot, yes. Fantastic.
Well, they use the parrot as it would be novel to the reed warblers, so they wouldn't have seen one before, but it also wouldn't be threatening. So that was a good model for that. They set about observing how different birds responded to each one. And after establishing a baseline for how each set of birds reacted, they allowed the birds they studied to see how neighbouring birds reacted to these models. Now, if the birds are learning through social stimulus, if they're learning from other birds, then the mobbing would only increase in response to the model that their neighbours mobbed. So if their neighbours mob the cuckoo model, then they should mob the cuckoo model. If the neighbours mob the parrot, then they should mob the parrot. But what they found was that when the neighbouring birds mobbed a model parrot, which they could be made to do by playing that sound at them, it made no difference whatsoever to how likely the birds that were being studied were to mob either a cuckoo or a parrot. but when a cuckoo was mobbed nearby, the rates of cuckoo mobbing greatly increased. In fact, naive birds that had not mobbed a cuckoo before would only start mobbing after watching their neighbours do so. And this is probably because female cuckoos have a sort of designated area in which they lay eggs. So a cuckoo in a neighbour's nest suggests an imminent threat to you.
So really, they're just copying their neighbours, but only when their neighbours have got it right.
Yes, and that's the key thing here. It suggests that the warblers are primed to learn new behaviours, but only when these behaviours respond to genuine threats. It's a really nice finding, and it's also been seen in things like macaque monkeys, only learning to respond to a threat when it's genuine. And they learn to be scared of snakes, but you can't teach a macaque to be frightened of a rabbit.
Really, I just love the idea of these guys wandering around the East Anglian fens with a parrot, a model parrot, trying to scare off the reed warblers. Fantastic stuff indeed.
And a plastic cuckoo on a stick. Now, also in the news this week, the winners of the Gruber Prize for Cosmology have been announced. It's the 10th anniversary of the Cosmology Prize, and this year it's shared between 3 winners. They were Wendy Friedman, who's the director of the observatories of the Carnegie Institution of Washington in Pasadena, California, Jeremy Mould, a professorial fellow at the University of Melbourne School of Physics, and Robert Kennicott, who's director of the Institute of Astronomy here at the University of Cambridge. They're sharing the $500,000 prize for leading the teams that measured the value of something called the Hubble constant, and that's the rate at which the universe has been expanding since the Big Bang. We're actually joined by Professor Robert Kennicott now. So, hi Robert, thanks for joining us.
Thank you. Happy to be here.
Well, you must be really pleased to see your work recognised by such a prestigious award.
Indeed. In fact, the phone call was quite a surprise, but the work was very influential. It was done about 10 years ago. I think the organizers of the prize were probably waiting to see whether we had gotten the right answer or not. In any case, it was delightful to have it recognized in the way it was.
I can imagine. So, what is so important about this number, the Hubble constant?
Yeah, the measurement actually ties into a whole series of experiments that many of your listeners probably have heard about over the last decade to try to characterize the expansion history of the universe. Our measurement actually provides some very basic numbers. How large is the universe? What is the distance scale? And in fact, it indirectly provides a measurement of the age of the universe. But moreover, it was when you combine it with other measurements, for example, of the supernovae at high redshift, it actually was the work that provided this strong evidence for dark energy in the universe and an accelerating expansion. So these experiments all tie together and yield consistent results. And this was one of the cornerstones of that series of experiments.
And so without this research, we wouldn't be asking the questions that we're asking today. It really was a major step forward in understanding our universe.
That's right. I can give a simple analogy. The measurements that established the existence of dark energy actually tell us how the expansion rate of the universe has changed. It actually slowed down and then it sped up over time, whereas we're measuring the absolute scale. And it's actually a difficult measurement. If you imagine, for example, you've looked on the television the last couple of days, you've seen many images of Barack Obama standing next to Nicolas Sarkozy and Gordon Brown. You can instantly, when you look at the screen, tell which of these people is the tallest, that Obama is the tallest, and you can even get, when they stand next to each other, get some idea whether he's 20% tall or 10% taller. But it's very difficult just looking at the monitor to have some idea how tall these people actually are, whether Obama is 6 foot tall, 6.5, 5'8", and so on. And that's our experiment was really designed measuring relatively nearby galaxies and providing the yardstick, if you like, next to these galaxies to actually measure the exact distance, of the quantitative distances and the scale of this whole expansion.
And will it also help us to understand what the ultimate fate of the universe will be? If we know more about its history, then surely we can predict a bit more about its future.
Indeed. Prior to this work, these distances were only known to about a factor of 2 accuracy, and in fact the best measurements at the time gave an age of the universe derived from the expansion that was younger than the ages of the oldest stars we could measure using other techniques. the result of these measurements combined with more distant supernova cosmology experiments actually led to several independent measurements of the cosmic age scale that now agree. We've actually over-determined the problem, and remarkably, these discrepant measurements have come into almost exact concordance. And it's almost unsettling. In fact, scientists, especially astronomers, are not used to precise agreement. The term precision cosmology, which is a new term, is something we're still getting used to. And the result of that is the implication, in fact, is as the universe in the future, the universe is actually going to speed up its expansion over time as this dark energy becomes more and more important force in driving the expansion of the universe.
So, how did your teams actually measure it? It seems like a very difficult thing to come up with.
Yeah, it actually boils down to fairly mundane measurements. What we want to do is survey distances to galaxies. We want to measure how far they are away in miles or kilometers very precisely. The key instrument that enabled this breakthrough was the Hubble Space Telescope. We use the key technique we use is a class of variable stars, pulsating stars called Cepheid variable stars, whose brightness can be measured accurately when you measure their period of oscillations. And Hubble actually had the resolution to actually be able to identify these stars in galaxies at distances of up to 50 or 100 million light years, and a light year is 6 trillion miles, so these are vast distances. And it was by we essentially laid out about 20 benchmarks and distances in the local universe, and we're able to measure not only the local expansion, but how that expansion actually changes with distance. We live in an overdense part of the universe that has affected the local expansion, and we had to calibrate that out as well. At any rate, so you can think of us sort of being as surveyors, laying out benchmarks and establishing a scale. Our result was accurate to about 10% at the time. Since then, other techniques using cosmic microwave background have repeated that measurement completely independently, and the two sets of results actually agree within a few percent. So we're quite sure we've got it right.
That's astounding. And so finally, the prize money shared between the three of you, $500,000. Does this go towards more scientific research, or are you planning a well-deserved treat for yourself?
You're not the first person to ask. And these important decisions take time, you must understand.
Of course.
So I can tell you I'm not going to buy a supercar. I'm not going to give it all to charity, but I'm going to spend some of it on one major party for the team.
Wonderful. Well, just in case you happen to be doing the invites at the moment, then you can write to the Naked Scientist at Cambridge University. But no, of course, we wouldn't expect an invite like that.
Anyway, I don't know. I'm a fan of the show, so who knows?
Wonderful. I'll keep an eye on the post. Well, thank you ever so much for joining us, Robert. That was Professor Robert Kennicott. He's the Director of the Institute of Astronomy at Cambridge University. And along with Wendy Friedman and Jeremy Mould, he's just been awarded the Gruber Foundation's Cosmology Prize for measuring the rate of expansion of the universe.
Lifting the lab coat on the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Ben Valslow and Helen Scales. And there's also another way you can listen to The Naked Scientists, and you can chat about the science in the show with like-minded folks at the same time. And that's in the virtual world of Second Life. We're live at 10 a.m, Second Life, every Sunday. So if you want to join us, sign up for Second Life, visit the Scilands, and then just have a search for Naked Scientists, and you can drop in on our mansion, relax on one of our sun loungers, and listen to the show.
Now, today's show is all about architecture and the science that goes into designing and manufacturing our buildings. Still to come, we'll find out how the show homes of the future could be printed out by a giant 3D printer, and how to make the best of the natural light available to your home.
But first, Ben and Dave have an experiment for you to do at home, and they're going to give you a bit of a challenge. Let's see what they're doing.
For this week's Kitchen Science, we decided, seeing as the show's all about architecture, that we'd look at materials and the properties that you need those materials to have in order to build things out of them. So, Dave, what are we going to build?
Well, a really important thing when you're building any kind of building or any other kind of structure is spanning gaps. So that we'll try and build a bridge.
OK, so we're going to build a bridge. Now, I'm guessing you're not going to be using large bits of wood, bricks, steel girders, but this is actually something that people can do at home.
Yeah, I thought we'd just basically try and build a bridge using a piece of paper, just a normal piece of A4 writing paper.
It's going to have to be quite a small bridge.
Yep, I figured we'd build a bridge as long as a piece of paper is wide.
Okay, and it's an A4 piece of paper. If I remember rightly, that means it's 21 centimetres wide. And we're going to make a bridge out of just a single sheet of paper. We can't pile them up and glue them together and sort of make a papier-mâché bridge.
You can just use one piece of paper, but you can fold it up and use a sensible amount of sellotape.
Okay, now, I am not convinced that this will work without entirely covering everything in sellotape. If we put a piece of paper across your gap, just place it there, well, it's held itself up, but I bet that couldn't take any weight. As soon as you touched it, it fell through. So this is quite a challenge.
Yes, it is, but the thing is, the paper didn't fail by breaking. Paper's actually incredibly strong stuff. In fact, both of us, if we clamped this right, we could both hang off this sheet of A4 paper with no problem at all. So the trick is using the strengths of paper in the right way. You can do things like rolling it up or folding it and try and make a stronger structure.
Okay, so there must be tricks that you have up your sleeve. But once you've done your rolling or your folding, whatever origami it is you're doing to build a bridge, how are you going to test it?
What I've done is I've taken a bottle, chopped the top off it, and tied a piece of string onto it. So you can hang the bottom half of the bottle from the piece of string. And my plan is to fill this up with water slowly and then see at what point the bridge breaks and then weigh the bottle, see how much water was in it.
Brilliant, so that way we'll be able to see which one can actually take the most weight. So please have a go at this at home. Find yourself an appropriate gap. We're actually using 2 box files standing up next to each other. And carefully fold some paper and see what makes the best bridge. We'll be back later in the show with our paper bridge designs.
So, what shapes will make the best bridges? Have a go at home and let us know what you think it is. Chris at thenakedscientist.com.
Now, while you're having a think about how best to fold a piece of paper to make a fantastic bridge, our next guest actually has been thinking about a rather larger problem, and that's how to build houses using a printer. Or at least he's hoping to do so soon. Rupert Saw is from Freeform Engineering, where he uses computer-aided design and rapid manufacture techniques to build walls and structures, which essentially amounts to using a gigantic 3D printer. Hello, Rupert. Thanks ever so much for joining us.
Hi, Ben. Hi, Helen.
So, Freeform Engineering, who are you and what do you do?
Well, essentially we do rapid prototyping, and with a slight speciality in that we focus on the construction industry, and in particular on those large-scale elements where we're really printing big things.
So, rapid prototyping, I'm guessing the name gives away what it is. It's for making a prototype very quickly.
Yeah, kind of. That's where it started. There's additive manufacturing, layer manufacturing. There's many different terms that are applied to this technology. All of them essentially similar. Taking a material, squirting it, pasting it down at one layer at a time, and building up a 3-dimensional object over time.
Now, I would assume that normally this is used for things like new designs of mobile phones or perhaps things that you hold in your hands.
Absolutely. Typically plastic things, but, small metal components, things that, mobile phones, automotive, aerospace, very, very common.
But you're thinking of much, much bigger things.
Yeah, and one level. I mean, part of it is actually bringing this into this awareness of what this technology is into the construction and architectural and design sector. And so trying to inform and bring about a new capability. Architecture itself is producing more complex designs and more interesting designs in the buildings that we see around them. They are able to generate amazing structures and forms in a computer, and the challenge is then how on earth do we actually fabricate those? How do we make them? They get stuck in the computer nowadays, these designs do. And so these printing technologies just work layer by layer, printing one layer at a time. And in fact, there's no great magic involved. If you look at how any house is built, it's all built with layers of bricks. And the reason it's built with layers of bricks is that we can build the bits inside as well as the bits outside. So this technology is really cool because it allows us to print the really complicated stuff inside at the same time as everything outside.
Of course, and the complicated stuff usually would mean greater expense because it takes more time and more expertise.
If you were talking about traditional engineering and manufacturing and trying to machine something out of a solid block, to try and get inside it, it's damn near impossible in most of the best of times. But, you can really get into these structures and make them really complicated and do quite remarkable things.
One of the key things in buildings nowadays is all about using the right materials, and we've talked on the show before about things like thin layers of wax inside little capsules that melt when you get to a certain temperature and then solidify again, and to use this as insulation. Are you limited with this sort of rapid prototyping as to what materials you can actually lay down?
Yes and no, like all things. There's no one ubiquitous process that does everything, but essentially if you take your DeskJet printer and literally scale it in your mind, and instead of ink you're putting through cement or gypsum, let's say, then you're somewhere close to where we're going with this. And it seems almost strange to think that you could squirt cement out and it wouldn't slump all over the ground, but that's because cement is used in moulds at the moment and concrete, and it's designed to be sloppy, and you take out those retardants and things like that, and it starts to set quite quickly. So very, very quickly you can build up three-dimensional structures, very, very big ones, if that's indeed what you're into doing.
So I think you've given us a very good image of how it works, but right now I'm sort of picturing a giant frame with an inkjet type head, effectively a bucket with a hole in the bottom that you control, that moves forwards and backwards in 3 dimensions and releases your material as and where you need it.
Yeah, if you've ever seen a large crane working in a shipyard, I mean, most people have got an image, that's a big crane, and it's placing big things, and that's kind of where this is going. Large crane systems or gantry systems that can have deposition heads or squirty heads that are squirting stuff out and building them up. But that's kind of a very simplistic level. As this technology evolves, then one very, very large machine very, very quickly becomes many, many small machines, and then you're into autonomous robot swarms and all of that wonderful future that lies ahead for us.
It's a lovely idea that building sites might one day just consist of robots that can get it done over and done with really quickly, no wolf whistling, no builder's bums.
That's it. It's quite simple, it's not hard to squirt things out and build things. Ask anybody that's made a cake with icing sugar. It's dead straightforward. But getting it, in swarms and collective agents, and then you open up a whole new world of possibilities and what you can build.
So effectively, because of the way that you can do this layer by layer, you can do the whole thing in one run. You don't have to print the outside walls and then take your machines inside and print in all the inside walls. You can actually just say, this is the design of house I want, go.
Yeah, now the whole point of this is that traditional construction is a very hierarchical thing. You start by putting the superstructure, and gradually with first, second, third fixing, you come down in resolution, if you like, till you're literally fixing the screws and nuts and bolts into the structure. And so it's a very top-down approach. When you're printing a structure, then and printing all the channels and ducts within the walls as well, and then you've essentially got to do the whole thing, all scales of resolution at the same time. So you've got to print fast to get your materials down, but at the same time you've got to print really fine to print all those little channels and ducts. And that's the key to it. As a friend of mine says, the real estate of the future lies between the walls in our homes,
right.
Those two surfaces. And at the moment they're essentially solid, but very quickly we can engineer those walls and fabricate and essentially fold what's more functions into much, much smaller spaces. And that's the real key to where this drives forward.
This is fantastic stuff. How is the cost likely to compare to traditional building?
Cost, you can never compare what is essentially something that's been going for 2,000 years. It's I'm not going to beat a brickie, and I was one myself, and we could work fast. What this does is it enables other abilities, things that a bricklayer can't imbue into a building. So if you're laying bricks, let's use that example, then you're good with straight lines and squares and fairly uniform shapes. A printer, if you ask it to print a squiggly line or a square, it doesn't care. It makes no distinction. Essentially, you can print complicated shapes and structures and forms. There's no cost involved in how complex the structure is. Now, that's a fundamental difference between how existing construction is and what it could be. So we're not usurping existing construction by any means. We're just going to add to those capabilities. So a lot of the key discussions are about sustainable construction, natural ventilation, I know you've got covering in this program, and what we're able to do is actually fold the actual structures and channels and functions into tight and tight spaces in these walls and actually make and design structures that truly can capture energy from the environment. And people know me for termites. I'm a bit mad like that. But, that's where we're kind of going with walls as membranes and not barriers, if you want a quick soundbite distinction there.
This all sounds fantastic, and I hope that we will see it in building sites in the very near future. That was Rupert Saw, Director of Freeform Engineering. He was explaining how one day you might just select the house that you want on a computer screen and then let it print out. He will be with us for the rest of the show, so if you have any questions, do feel free to ask. You can email them to chris@thenakedscientists.com.
Keeping you abreast of the world's best science. The Naked Scientists.
You're listening to The Naked Scientists. In just a moment, we'll be finding out how the natural light entering a building can be controlled to save energy. But first, we joined Mira St-Fillingham, who's been out in London this week, in search of another way to make buildings more efficient.
In the UK today, 40 to 50% of our energy is consumed by buildings. And buildings that use air conditioning typically use double the amount of energy as ones that don't. But one way to reduce this consumption is by designing naturally ventilated buildings, which don't need air conditioning to keep them cool. So this week, I'm at the School of Slavonic and Eastern European Studies on the campus of University College London. In 2005, this building was constructed and designed as a low-energy building. So with me this week is one of the senior researchers that helped design the building, and that's Sean Fitzgerald from the BP Institute. So Sean, this building was designed to have natural ventilation. What does this mean exactly, and why does it help keep a building cool?
A naturally ventilated building is one which is trying to use the forces of nature to get air from within the building to without, and to actually distribute the air within that building as well. So we're looking at wind and buoyancy as the primary driving forces. A mechanically ventilated building uses fans, and a mechanically ventilated building would typically have one where the windows are not openable, so you have to use fan power throughout the year. And when you look at the amount of energy that we're using with fans compared to wind and buoyancy, the numbers are staggering.
So we're outside the building now, and just looking at it, it's reasonably large, and it's got 4 what look like metal chimneys on the top. So what are these as part of the design?
So the chimneys on the front of the building here that we're looking at are exhaust chimneys. They are there to try and allow the hot air that's been generated within the building to be extracted, and it's using, in this case, mainly buoyancy to drive that air. Those chimneys are to remove the hot air and then the odours associated with that hot air in the building.
So as well as these chimneys that are located on the top of the building, what else has been incorporated into the design of this School of Slavonic Studies to keep the airflow moving?
Well, one of the big challenges with a building in the middle of a city is the intake air. And the intake air has got 2 challenges associated with it. One is if you open vents at low level, there is ingress of noise from a noisy street, such as the one we're on. And secondly, it's to do with air quality. And the fumes from taxis and cars can be easily drawn into buildings. So if you can create openings at high level and bring the fresh air in from high level, you can help overcome both of those challenges. 20 metres up in the air, 25 metres up in the air, the actual sort of dirty air syndrome isn't as significant as it is down at street level. In this particular building, the air intake path at high level feeds an atrium, and the atrium itself is large relative to some of the other chimneys that we've got around the perimeter of the building. So the air intake path is through the centre of the building, and this is to help provide acoustic treatment of that air, just using the natural fabric of the building. It's just glass.
So we're just going to move inside now to have a look at this atrium and understand a bit more about how it works. So we have entered the building now, and there is a central atrium, which is very large, running through the core of the building. It's 6 stories high, and the shape is an equilateral triangle, of which the sides are probably about 5 to 6 metres long. So, Sean, this is a very large atrium.
It's a wonderful centre of the building architecturally, and it provides a number of functions as well. Firstly, you'll notice that the daylight provision within the middle of the building is significant, but it's not bright direct sunlight. It's a background diffuse radiation, so it's a really lovely sunlight that you're getting into the building. But obviously the second function that we cared about as engineers is that this is the air source for the building. And you'll see that around the perimeter of the atrium, on every floor, there are a number of openable windows, and if you look closely, those openable windows have got a chain attached to them and a motor. So these are motor-driven actuators to control the amount of opening area between the atrium and each of the occupied spaces, the offices and the library.
How does this atrium and the chimneys on top of the building all now just work together in order to keep cool air flowing through this building?
The building ventilation works primarily because there is heat being generated within the library and the offices through lights and IT equipment and people. So the heat that is generated from that source will ensure that any fresh air that comes into the space is reduced in density. It then therefore becomes buoyant, and it will then rise out through the perimeter chimneys, the chimneys that are around the backside of the building here. And we now have a U-tube effect where fresh air is being pulled in through the middle of the atrium at external temperature conditions, in through these windows, where it is then heated, and the hot air then rises out through some of the chimneys that we saw out through the front of the building. So it's using the heat within the building to actually generate the airflow, and the airflow itself managing the temperature build-up within the building.
Now, there are actually sensors in the building as well that are in action in order to help control just how many things need opening. So what sensors are they, and what are they looking at?
The sensors in this building are temperature and carbon dioxide. The challenges of ventilating a building are to make sure that there's enough fresh air coming in, so the proxy that we use is CO2 level within the building. And the second function is to make sure that it doesn't get too hot in the building. And both of those parameters, internal temperature and carbon dioxide levels, are used by a control system to regulate the amount of opening area of these openable windows that we have.
Now, we are in London, so it doesn't actually get hot that much during the year. So it's generally colder than it is hotter. So what about during winter? What about when the weather's cold outside?
When the weather's cold outside, the same strategies are deployed for this building. But as the fresh air comes in through this atrium, you'll notice that in front of all of the opening windows there is a radiator. So the radiator in this building is being used to preheat the incoming air. But on a moderately cold day, most of the heat being delivered to that air will be by the lights, the heat, the people, and the IT equipment.
Now, this building did open back in 2005, so have there been any other newer buildings being developed which are slightly better designed?
One of the things that's effectively been the Achilles heel of these wonderful naturally ventilated buildings is the fact that we've been using radiators to preheat the incoming air. But when one looks at the amount of heat generated within modern buildings, we find that it's considerable and easily enough to maintain the interior at an adequate level of, say, 21 degrees C for all but the very coldest days. And that technology will allow naturally ventilated buildings to have even lower energy consumption levels than the ones such as this exemplary building that we're in today.
That was Sean Fitzgerald from the BP Institute in Cambridge talking to Mira Synthillingham. Now, we've heard how energy can be saved by removing the need to turn on your air conditioners, but another feature we're looking at for the future of buildings is the controlling the natural light that comes into a building and the heat that's lost through all the different surfaces. Now, Stephen Gage is a professor of innovative technology at University College London, and he's investigating the use of thermal shutters to control the amount of light that enters a building and also the amount of temperature and heat that's lost. So, Stephen, thanks for joining us.
Hi, good evening.
Hi. What made you come up with this idea for thermal shutters in the first place?
Well, I have to say the idea is not new. It's been sort of put forward in the States in sort of the 1970s, 1980s. But the reason that I came back to it was I was looking at retrofitting thermal insulation onto typical Victorian buildings. And I realised that these buildings had windows which were larger than equivalent buildings today. And I think that you've probably seen sort of new housing developments going on around our cities, and you realise that the windows there are getting smaller and smaller. And the reason is that windows let through a lot more heat than solid walls, modern solid walls, by anything up to a factor of 5, 6, 7, 8, 9 times. So in order to get buildings not to kind of lose too much heat, there's a real pressure on architects and designers to reduce window area.
Yes, I live in a Victorian house and I love the fact that our windows are nice and big, but I do worry that we lose a lot of energy, heat across them because they're not double glazed. So what are these thermal shutters going to do to help that?
Well, the situation applies, I think, generally that we live in houses traditionally where we use windows to let in light. As the windows get smaller and smaller, we have to put our lights on and we start using energy in lighting. Then we get rather nasty, to my mind, low-energy fittings to get round that, and we're in some sort of vicious declining spiral. And it struck me that perhaps one should look at the idea of turning our windows into walls when we're not there. And this is really quite interesting in research done by a colleague of mine, Alexei Marmot, for example, in offices. Convincingly shows that we're not in our buildings for an awful lot of the time during a 24-hour cycle. And indeed, we are in our homes, for example, at night, when there's no external light. Now, this all leads to the possibility of thinking, well, perhaps we ought to put thermal shutters on the outsides of our buildings, to essentially turn the windows into walls when we're not there.
And we've had shutters on traditionally on buildings made out of wood. Presumably you're thinking of using something a bit more advanced than that.
Yes, the kind of materials that we're looking at are the kind of materials that go into modern, highly efficient fridges, and especially fridge doors, where you can get the equivalent thickness of a traditional, of a well-insulated wall inside something like sort of 25, maybe 30 mil, maybe 40 mil, that kind of thickness, which makes these really not terribly big beasts to open and close.
And is the idea that you would open and close them yourself, or are they going to know when to do it themselves?
Well, obviously, the interest would be to have the things opening and closing on their own, but if they do this, they have to have either some knowledge of your presence or the possibility that you can override them as they go on their way. Because I think that one thing that one has to say is that when you're in a space, say in your large Victorian living room, it may be a bit cold outside, but if you're there and the weather's beautiful, perhaps you don't mind losing a bit of heat through the window.
So it will be able to control itself to some extent. And this will help us both in summer and in winter, will it?
Well, that's right, because obviously shutters that stop heat, as it were, getting out of a building, will stop heat getting into a building, and especially they'll stop solar gain.
And also the idea of the fact that we're not in our buildings very much of the day, is that going to become a point where the window's going to know that you've gone home at the end of the day?
Well, I mean, there are plenty of sort of intelligent systems that can tell the window that. You can even tell the window that you're coming home. I mean, people do this all the time with building management systems. It's not a big deal.
And are we already seeing these thermal shutters in use, or is this just still in development?
We've got a project where we're taking these forward in development to go for a product with a commercial company. There aren't any standard products at the moment, although architects have used sort of commercially available doors to try and achieve this effect.
Fantastic. Well, thank you very much, Stephen. That was Stephen Gage from University College London explaining how automated thermal shutters could help us reduce the amount of energy lost through our buildings, cutting down our energy requirements and saving money.
Laying the facts bare. I say. The Naked Scientists.
And now you are listening to The Naked Scientist. It's time for our question of the week. So we've invited Diana O'Carroll to join us in the studio once again. What do we have this week, Diana?
Well, this week we're going to prepare for a deep impact.
Hi, this is Mike calling from the United States in Tucson, Arizona. Love your guys' podcast. It's great. What I was wondering was what would be the short and long-term difference if a significant, like a dinosaur-killing type asteroid or meteor would impact the Earth in either a land mass or in the deep ocean or polar ice cap.
And using a nifty bit of asteroid impact software, this is what our expert came up with.
Hi, I'm Heather Jackson and I'm from the National Museum of Wales. Well, if we imagine the size of this potential asteroid, it's perhaps 10 kilometres across, similar to the size of the one which fell in Mexico 65 million years ago. Wherever it hits, it's going to be incredibly destructive. The most devastating impact is likely to be in the ocean because it could potentially cause tsunamis, and the least destructive would be if it were to hit a poorly populated area, perhaps like Antarctica. But the size of this object is something the size of Cardiff, travelling at 25 times the speed of sound. The compressed column of air travelling in front of it would heat the ground to almost as hot as the surface of the sun, and the blast wave would kill anything within about 250 kilometres instantly. But the real killer would be the long-term atmospheric effects that would be caused by the vaporization of rock, particularly if that rock contained large amounts of sulfur, because that could lead to severe acid rain. Predictions as to the size of the waves produced if it fell in the ocean vary, but it's clear that a large impact would drown coastal areas, which is where most of our population lives. So the Pacific coast of Asia is a particularly deadly place for an asteroid to strike because of the population density there and the potential for tsunamis. Overall, the worst effects would be caused by a meteorite falling into an ocean, perhaps not particularly deep, about 2 kilometres deep, causing a tsunami and then vaporizing seabed sediments, which contain a lot of carbon dioxide and a lot of sulfur, which would cause climate change for years to come.
So if you're going to tell your incoming asteroid to go anywhere, you'd probably send it to the North Pole, except that's where the oil is. So maybe the south instead.
And on our forum we had all sorts of wonderful suggestions. Madius Scientica will be hiding out in his underwater city. Turnip Sock suggested the Sahara, and in fact we might make a lot of glass that way. And one writer called Ethos agreed with our expert that a polar ice cap is the best landing pad.
I like the underwater lair idea best, and from things careering into Earth to things escaping.
Hi, this is Nigel, and I've always wondered, is the Earth leaking? Could water evaporate into space? And given enough time, could the Earth end up like Mars, a desolate wasteland with not a drop of water to be found?
Where does all the water go, and do we need to install a giant umbrella on the planet to stop it raining outwards? Give us your thoughts by email, chris@thenakedscientist.com, or via the forum at thenakedscientist.com/forum.
Bringing the facts to bear. The Naked Scientists.
You're listening to The Naked Scientists. Now it's time to get back to our kitchen science. We've heard from a few people on what they think the best way of building a bridge might be. John in Peterborough thinks a concertina would be the good thing to go to. In Second Life, we've heard from Troy McClure, who says it could be a triangle cross-section. And Darley Wave Rider thinks it could be corrugated. So shall we go and find out what's going on?
Welcome back to Kitchen Science. Today we're making bridges out of a single sheet of paper. Now we've made ourselves a chasm using two ordinary box files. They're 21 centimetres apart. So Dave, we tried this earlier. We laid a sheet of paper across the chasm and it fell in pretty much under its own weight. But you think that you're going to be able to hold quite a bit of weight with paper. So why didn't that work?
Well, the problem is not that paper's weak. The problem is that paper's flexible. And so if you're trying to make a beam out of a piece of paper, it just bends and falls down. And the reason why paper is so flexible is essentially because it's so thin. What happens when you bend something is the outside of the curve gets stretched slightly and the inside of the curve gets slightly compressed. The only way something can resist being bent is by being very stiff and resisting this extension and this compression.
And because it's so thin, it means that the difference between the extension and the compression is really small, and so there's no resistance.
Yeah, that's right. And the trick to making a good strong beam is to make it deeper without weakening it in another way.
One thing that does look like it does a very good job of making it deeper is you folded the paper into a square. It has a square cross-section.
That's right. We can give this a quick test.
So we'll put this across our bridge, and we have our plastic bottle, and we'll tie that on. So this is just the plastic bottle. We haven't put any water in just yet. Now it's holding the bottle easily. It's looking very good, actually. Now let's pour some water in and see how well it does. Ah, right. That didn't take very long before it folded flat and then fell down, and that would have really made a rubbish bridge. How much weight did it take?
It took 146 grams of water. The problem it had was that squares have a weakness, and that's that you can take a square and turn it into a parallelogram without changing the length of any of its sides. So all it did is it sort of folded over sideways, turned into a parallelogram, at which point it goes weak and then it collapses.
How can we improve on that?
Well, one way of avoiding the failure mode of the square is to make a triangle instead, because a triangle can't collapse sideways. So we can try a triangle.
OK, so this one is again made from a single sheet of paper, but in cross-section it's folded into an equilateral triangle, probably about 5 centimetres on each side, and it easily takes the empty bottle. But now let's see how much water it can take. And there it goes.
So this takes about 290 grams of water. Not bad.
And much better than the square cross-section we had.
Well, the problem with this beam was that the big flat sides of the triangle were essentially too flexible. They can still bend in the way that a normal sheet of paper does, and that made it quite weak. Now, another shape which is quite commonly used for building things with, which avoids that problem, is the tube. Now, the advantage of a tube is because you've already bent it in one direction, the paper can't bend in another direction. In order to do that, it would have to change its length. And so this should make it quite strong.
OK, so let's just roll a bit of paper up into a tube. Again, a single sheet of A4 paper, and we'll just tape it closed to stop it from unrolling while we're putting our weight on it. Let's see how well this does. Let's see how much weight it can take. Right, as you're doing that, I can see from the sides that it's sort of going elliptical. It's starting to flatten itself out, but it's taking a lot of water. Good catch, Dave. OK, so It eventually went. It seems to have taken a lot of weight. How much is that, Dave?
That's about 1.2 kilos.
So really, rolling it into a tube makes a really big difference.
Yes, it does, although even that wasn't ideal, because the problem was the tube wasn't being loaded the way tubes like to be loaded. If you've got a tube, it's really good at supporting a compressive force, a squashing along its length. That's because in order for it to fail, it's got to bend. For it to bend, some part of the paper's got to get longer than it was before, and paper doesn't stretch, it's very strong, so you can actually squash a tube and apply really quite large forces to it, and it won't break. The trick is to come up with a design where the tubes are always in compression, and one trick is to make a triangle out of tubes.
Now, Dave prepared this earlier on in true Blue Peter tradition, and this is 2 tubes of paper, each made from less than half of a single sheet of A4 paper, and they are sellotaped together at the top, and then across the bottom there's just a strand of paper which hasn't been folded, it's just flat. And now he's standing it up on our bridge, so this is either going to be a big wet mess or a glorious success. When you're ready, you can let go. And that's actually easily taking the 1.2 kilos that the single tube took. And this is, again, a single piece of A4 paper. Our bottle is already nearly full, but I'll just add a bit more water to see if it can take it. And that's right up to the edge. If I put any more water in, it will overflow. Dave, that's a brilliant structure. That really works well.
Oh, I can even pull down quite hard, as well as the nearly 2 kilos on the end of it. It's not going anywhere.
Okay, so this is the trick of using the right properties in the right places. We're using the tubes under compression, which they're really good at, and the bit across the bottom is under tension. And as you said earlier, paper's actually very strong, so the tension won't give way either. Is this why we see similar shapes, these triangular structures of tubes, in real bridges?
That's right, real bridges and lots of buildings as well. But yes, a triangle where all the corners aren't rigidly attached to each other, the tubes are always in compression, you can work everything out, you can design everything beautifully and make a very, very strong light structure.
I think people should give it a go at home.
That's right, if anyone wants to have a go, see if you can beat 2 kilos with a sheet of paper across a gap and not too much sellotape, that's cheating.
OK, so no cheating, but please send in your photos and your designs for bridges made of a single sheet of A4 paper and let us know how much weight they can take. We'll put them all on the website at thenakedscientist.com/kitchenscience, and why don't you see if you can build the strongest bridge? We'll be back with more Kitchen Science very soon.
So please do send us any pictures or designs for single-sheet A4 bridges. See if you can suspend more than the 2 kilograms we managed to over a 21-centimetre gap. And Dave was confident that his last design could take double the water we were able to weigh. So perhaps you can have a go at beating him and designing an even better bridge. We'll put everyone's ideas on the website at thenakedscientist.com/kitchen science. And next week, Dave is live in the studio with a really simple experiment. All you need is a strand of uncooked spaghetti.
Well, that's sadly all we have time for this week. Many thanks to Robert Kennicott, Rupert Saw and Stephen Gage for joining us on the show. And also thanks to Sean Fitzgerald for sharing his story with us. Thanks to our production team, Diana O'Carroll, Mira Senthilingam, Tom Simpkins and Dave Ansell. And finally, thanks to all of you at home for listening. Next week is one of our Q&A shows, so get all of your science questions and your spaghetti ready. As usual, if you've got any questions for us, get them into chris@thenakedscientists.com. And if you'd like to hear the show again or catch up with any old shows that you've missed, you can download the Naked Scientist podcast for free from thenakedscientists.com/podcasts. So have a great week and goodbye.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientist.com.